Barry Colford. Barry was previously Chief Engineer and Bridge Master of the Forth Ridge Bridge in Scotland, and is now at AECOM North America. He's been there since 2014, and he leads their complex bridge preservation practice from their Philadelphia office.
Thank you, Tom. Good afternoon, ladies and gentlemen. As you probably can tell from my accent, I'm not a Philly boy, but that's where I'm based at the moment. Of course, the Eagles winning and Villanova winning, which is close to where I live, is great for me. I lead, my name is Barry Colford, as Tom said. I lead AECOM's complex bridge preservation practice. And I've spent most of my career on suspension bridges and cable-stayed bridges. And this afternoon, I'm going to give you some insight into the preservation of main cables. Just to give you an idea of cable construction, traditionally they've been aerially spun, as you can see in the left. The Japanese started introducing prefabricated parallel wire strands. That's Akashi, the longest bridge in the world, almost 2-kilometer span, 6,500 feet. Some are helical strand, as you can see in the right, but mainly they're parallel wire, about 0.192 of an inch or just under 5 millimeters as I would know it. And they're compacted together, and then they're galvanized, and they're very high tensile wires. And their very nature, although they look solid construction, there's about 20% of the cable is actually void. The global suspension bridge inventory, most of the bridges used to be in the US, but China has recently overtaken that in numbers. Japan, Norway, and Canada also have significant numbers of suspension bridges. But most of the old bridges, the older bridges, are in the US. You can see topography drives big bridge building. And you can see that North America in total has about 30% of the global inventory. And as I say, it's got a higher number of older bridges. The notable ones are Verrazano, Golden Gate, Mackinac, and George Washington. But there are significant other bridges of significant size and span. And you can see they're grouped fairly geographically on the west coast and throughout the east coast and parts round about the lakes there. The conventional protection of these cables, that shows a cross-section of it, has been the same since Roebling's time. It's to smear the wires with red lead paste, although that's now zinc paste, and then wrap a very soft 9-gauge wire around the outside and then paint over it. And you can see that in cross-section on both of these slides. The conventional cable protection is just to keep painting. The slide and the shot on the left, as you'll probably recognize the color. That, of course, was taken back, probably, judging by the hairstyle, back in the 70s. But unfortunately, what we've discovered is painting doesn't work. It isn't flexible enough to accommodate the movement of these bridges, because these bridges move about a lot, and painting cannot accommodate it. It cracks. You have crossed wires within the cable itself. At the cable bands and at places where we have to caulk and seal, water gets in. And it's caused a real issue over the past 30 years on main cables of suspension bridges. What we have been doing is providing access to look inside. And that might sound quite a difficult job, and it is, but once we've done it once, we can do it again. And what we do is drive wedges into the cable, and it opens up quite readily. You can see that in the top right, and inspect the inside of the cable. And we found things that we didn't expect to find. The North American bridges were started firstly. In fact, in 1945 was the first main cable internal inspection that I'm aware of, and that was in Brooklyn Bridge, way back in 45. But it's only in the past maybe 20 to 30 years it's gathered pace, and we've been looking inside these cables because we've been seeing some significant deterioration. That one on the left-hand side is Forth Road Bridge, and the one on the right-hand side is Severn Bridge in the UK. What's quite interesting about this, if you look quite carefully at some of these wires, these are broken wires. That cable at Forth looked in pristine condition on the outside. We'd painted it to death, almost. There was no sign of moisture, no sign of corrosion, yet when we opened it up, wires fell out because wires had broken. You can see in that cable on the left, it doesn't look that... Some of the wires still have their original galvanizing on them. Most of them do. But unfortunately, there are places in it, the cable, where breakages have occurred. There are cracks in the wires, and we've got broken wires. That's a bit of a horror story, the one on the left. That's from another bridge in the UK. I can't really say where it is because the client is very sensitive about it, as you can probably imagine, looking at what you can see there. But again, if you look at the wires and the cable, there's not that much sign of corrosion, certainly in places. But a meter away from one piece of really nice wire, there's a broken wire. And that we found in a lot of these cables. The image there on the right-hand side is a broken wire. These wires are taking about 1.25 tons of load. There's between 7,000 to 20,000 wires in a cable. They're all taking about the same load. Corrosion occurs, a crack develops, and the wire breaks transversely across, as you can see. And that's a cross-section of a corrosion pit plus a breakage. You can see in this slide. We calculate the strength loss. The inspection is to try and determine what the strength loss in these cables has been, and we found various stages. This went back to work done back in the 70s. We've got an NCHRP report which allows us to do that. We can sample and test wires, and we swage wires back in. You can see the ferrule on the top right-hand side, tensile testing, to try and get an idea of the strength of the cable as it is at the moment, because that's what owners want to know. And of course, when you carry out one of these inspections, you have to recompact the cable, and then you have to rewrap it, and that's a compactor on the left-hand side and a wrapper on the right. The bottom shows the last use of red lead paste, I think, outside of China, and that thing that was 2005 at Forth Road Bridge. So it's all galvanized paste now. But you can see that cable being recompacted on the left. It looks in great condition, but that had a significant number of broken wires within it. So water, moisture is getting in there despite our best efforts to paint it over a number of years. Just as a footnote, one of the interesting things is the strength of cable wire. I'm sorry, this is an MPa, megapascals, but 1,000 is about 150 KSI. And maybe Roblings knew what he was doing, because his wire was about 150 KSI, and that's about the point where hydrogen embrittlement starts to become important in wire construction. Now we're way up at nearly 1,800 megapascals. We're up near 290 KSI. And the problem is that the more, because we're bigger spans, we're trying to get more out of wire. There's always a downside in engineering. The stronger you make something, the less ductile it becomes, the more brittle it becomes, the more prone it becomes to hydrogen embrittlement and stress corrosion. That's the side effect, unfortunately, of trying to squeeze as much ultimate tensile strength out of the material. So what's causing this deterioration, and how do we stop it? Well, it's caused by two things. It's caused by corrosion, but it's also caused by, as I said, hydrogen embrittlement. And water is the key to both of them. Water will cause corrosion. It needs corrosion. Corrosion needs water and oxygen to happen. And hydrogen embrittlement also needs moisture or water to happen. You can see the hydrogen embrittlement cartoon down in the bottom left there for all of you who are chemically minded. That's one of the reasons I took civil and structural engineering, because I hated chemistry, but there you are, that's the formula. But what happens is that in high tensile wire, the grain gets elongated, and it makes it more susceptible to free hydrogen ions, positive hydrogen ions, going into the surface if we have water present. So we've got these two elements, these two actions happening: hydrogen embrittlement and corrosion. We've looked at trying other methods of keeping water out. We've tried oiling cables. Ben Franklin and Bronx Whitestone in New York were oiled. That's Ben Franklin on the left there. It's messy, it's expensive. You have to open up the whole cable and pour oil in. You have to ensure that you're getting all the oil into those 20% of voids along the full length of the cable. It tends to want to pond down at the bottom, as you might expect, and it dries out after time. Some people have tried wrapping cables, but my experience of that is you cannot effectively enough wrap it to stop moisture getting in. And what tends to happen is all you do is trap moisture within the cable. You can't keep it out, but unfortunately wrapping on its own tends to keep it in. That's my experience of it. So we're looking at something else to stop this happening, and we've looked at dehumidification. Dehumidification has been well known for a long number of years. It was way back in 1935 that Vernon did his work to discover that if you put a bit of ferrous material in a container and drop the relative humidity to below 40%, it will not corrode. It practically ceases below that level. And it's been used in bridges for a long time. It's been used in box girder bridges throughout the world. It's been used in anchorages. And the Japanese started using dehumidification in cables back in 1997 in the Akashi Bridge. They took the wrapping wire off after a few years and discovered some surface corrosion and decided to apply dehumidification. So they, in fact, invented this principle of dehumidifying cables. So how does it work? Well, it's really fairly simple. You can see, as I said, that there's maybe 20% of the cable is void, and all we're doing is passing dry air, not warm air, just dry air, with a relative humidity below 40% through these voids. We eliminate the moisture, which eliminates corrosion, and it eliminates hydrogen embrittlement because there's no free moisture for the hydrogen ions to form. And what we do is we produce dry air, pump it into the cable, and let it exhaust out what we call a blowing length, a length along the cable. And this was the concept that was invented in Japan way back in the late 90s, and it's now being used throughout the world. This is a fairly typical dehumidification system. The green is inlets, and the red are outlets, exhaust points and inlet points. We normally put the plant, if we can, in the anchorages of a bridge, and the pipe work, we have pipe work to feed the inlet points and blow air into the cable. What we do is to ensure that the air stays within the cable, we wrap it, and the material that we've been using, has been used in the majority of these bridges, is D.S. Brown's cable guard. It's overlapped, hand wrapper on the left. This is from Delaware Memorial, one of the Delaware Memorial bridges, which has just been completed. And it's hand wrapped. Sorry, I'll rephrase that. This is Chesapeake, judging by the colour. And then we put these blankets on to heat it, to seal it together, and the final wrapped cable is shown on the right. Now, I said before that I wouldn't wrap a cable without dehumidifying, because all the wrap is doing in this case is keeping air in. It's not there to keep moisture out. That's its primary job. We have to seal it, of course, and this is a seal that we've developed with D.H. Brown's assistance, and it's pretty effective. It seals at the cable bands and other areas, and it's all to keep the air within the cable. This is an injection sleeve just about to go on. The cable hasn't been wrapped yet. The old wrapping wire has been taken off for about 4 foot, and we put these zinc wedges, perhaps you can see them. We tease these into the cable just to get the air flowing within the internal surfaces of the cable. On the right-hand side there, that's an exhaust sleeve from Forth Road Bridge as it's coming up to the top of the tower. These are different views of exhaust. You can see the cable on the HDPE pipe that we use on the side of the cable there on a carrier wire, and various injection sleeves and exhaust sleeves as well. The plant is all off the shelf, dehumidifier in the middle. We use the concept of a plenum chamber or plant room. The plant is kept in a chamber. You can see it in the left. It's maybe 25 foot by 12 foot by 10 foot high. And what we do is that the air inside there is dehumidified to 40%, and it's kept at that 40%, and then it's pumped via the pumps in the bottom right, via these 2 pipes. You can see the 4-inch pipes coming out of the plant room into the cables. And there are 4 of these at the Delaware Memorial bridges. If you had a standard-sized bridge, you would probably only have 1 at each end. We monitor the flow, pressure, temperature, relative humidity, all coming out of the cable, and these are monitoring points, and so there's a SCADA system involved, and the SCADA system's implemented. You can see that graph, which is from one of the bridges we've recently done in the US, And the green line is the relative humidity of an exhaust location, and it started about 90%, and it's now down about 40%. So we're blowing dry air in at 40%, and eventually, after a period of time from March 2014 to January 2015, it dries out. It has this process or methodology or system has been used in a number of bridges throughout the world now. As I said before, it started off in Japan. It's now fitted to almost all that I know of new suspension bridges. I would have to say it's probably saved the suspension bridge form of construction, because without it, people were starting to build cable-stayed bridges with spans where naturally a suspension bridge would fall in. And I know from my own experience that the clients were looking away from suspension bridges because of the issues with main cable deterioration. So now we've got about 20% of the global inventory has been dehumidified. All the new Norwegian bridges, Turkish bridges, Chinese bridges, and that's where suspension bridges are being built these days, are all being fitted at the construction stage with dehumidification to the cables and the anchorages and box girders as well. This is just an example of water removed from one of the UK bridges over a 5-year period. A huge amount of, I think it was 600 gallons of water was coming out of the cable. So there's a huge amount of moisture is taken out of the cable. Some of the bridges have acoustic monitoring fitted, and that allows us to try and gauge the effectiveness of the dehumidification, not just from relative humidity drop, but from wire breaks, because a lot of the bridges had significant wire breaks. Severn Bridge and Forth Road Bridge had significant wire breaks, and after dehumidification was fitted, this is what happened. The thicker grey line is the dehumidification profile from all the exhausts on one of the bridges in the UK, and the dotted line is the wire breaks that were occurring, and they were occurring at a frightening rate on this bridge before dehumidification was installed. And I don't think it's a coincidence, just around 60%. When the relative humidity dropped to 60% in this cable, the wire breaks started flattening out. As I said, it's been used in a number of bridges now. It's kind of lagged behind in the US. US owners have been a bit reluctant to accept the technology, perhaps. The 3 big bridges in the UK have been done. Bridges in other parts of Europe have been done. AECOM designed the first system in Chesapeake Bay, and it's now been installed. It was up and running in 2015. We're just finishing the work in Delaware Memorial, both bridges there. It's being fitted in South 10th Street in Pittsburgh, and is slowly beginning to become more prevalent on US bridges. You can see the spread throughout the world, and it's taken 19 years to get from Japan to here to start being accepted in the US. Now, given that the main cables of a suspension bridge are the primary elements in the bridge, without those you do not have a bridge, then to fit dehumidification, and for a standard sized bridge we're talking $20 million perhaps, depending where it is. That's a significant investment, but it will extend the service life of the cables. To try and change, augment, or replace main cables in a suspension bridge is no easy task if you want to keep the bridge operational. This methodology ensures that there'll be no further deterioration. It cannot make the cable better. It cannot replace what's already been lost, but it stops further deterioration within the cables. We've learned that conventional means are not effective. Painting is not effective. I've been looking at this for 20 years, and I've sadly come to that conclusion. Water is the main cause of this deterioration, and it does, cable dehumidification does demonstrate a reduction in wire breaks as the relative humidity reduces. We're now beginning to rethink this basic concept of how we protect cables. Chesapeake has now been done, the 2 bridges there, Delaware has been done, the 2 bridges in Philadelphia are going to be done in the near future. our colleagues in New York might eventually get round to think that this is a good idea and perhaps we should apply it to our bridges, but that remains to be seen.
I'm Richard Kerr from Florida DOT. Just a point of interest, we do have one small suspension bridge in Florida, in northeast Florida, over the Suwannee River, which wasn't shown on your map.
Thank you very much. Could I ask a question
Sure.
of you? Have you looked inside the cable?
The district, I don't know if there's any District 2 people here. Our district that has it, I believe they have looked at the cable and done some rehab on it.
The cables are not actually a closed system, as what you were showing.
Thanks. And I should have made it clear that these were, I don't want to use the word major suspension bridges, but suspension bridges over 1,000 foot or 1,500 feet. It's the sort of larger spanned ones. There are plenty of smaller spanned cable suspension bridges, but they generally tend to not have parallel wire cables.
Yeah, when you say blowing air, is this air at ambient temperature, or you warm the air? Is there a temperature range that the air needs to maintain in order to move the moisture out?
No, it's ambient air is drawn into the chamber, into the plenum chamber, but it's not heated, so it goes in at ambient. I should have said that it goes in. The pressure it goes in is about 3,000 pascals, which is about 12 inches of water, because if you try and push it in any further, it just blows the seals. And we've found that that's pretty effective in drying out the cable. A cable, depending on how much corrosion's within it, how old it is, will dry out in maybe maximum a year at that sort of pressure. Some will be much quicker if they're newer, because the air will flow more quickly, but it will get to if there are voids within that cable, that dry air will drive out the moist air, and it will all go to the exhaust points.
Hi, I'm from Michigan, and I'm Dave Juntonen. Have you noticed a time frame from when the bridge was built to when they started having issues with the breakage and the corrosion?
It's a good point. I think it's difficult to say. Some people think, if you look at the life, what happens to a piece of wire when it comes out, the wire manufacturers, it's wound round a spool, usually. And that's one of the advantages of constructing it in strands. It's wound round, so it's already got a pre-stress in it when it comes to site. And if you've ever watched a cable being spun, you think the galvanizing can't possibly survive it, because the guy, they're trying, it's quite a difficult job, aerially spinning individual wires, and they're trying to get them into the saddle at the tower, and they're using pinch bars, and it does get quite a bit of abuse on site, no matter what you try and do. So there's been various thoughts, whether you say it's 10 years after construction, whether it happens as soon as it lands on the job site, or whether it's when it's being spun into the cable. I think it's very much depends on each individual bridge. But they're all galvanized, and one of the issues is that the galvanizing, once it starts to break down, seems to concentrate corrosion pits and fractures within the wires. Williamsburg is the only major bridge that doesn't have galvanized wires, and the failures there of the wire is quite different from what I showed earlier. It's almost a classic tensile going away to nothing before these wires failed, whereas with galvanized wires it's different. I know some of the details of Mackinac, of course. I spoke to Kim quite a bit on that. Every bridge is slightly different. Perhaps having no salt water, no industry has helped those cables, but I don't know. I don't know how much inspection's been done.
Do you have an idea of the service life of the dehumidification system, specifically the wrapping?
Yeah, DS Brown, I don't know if anyone's in the audience from DS Brown, but there's maybe 30 years for the wrapping. I think they say 45 years. Maybe that's not unfeasible. Like all mechanical and electrical plant will have to be replaced probably in 15 years. We had a real issue with sensors at the beginning at Forth. I was a kind of guinea pig as a client at Forth, and we were always having to replace sensors, but they have got much better. The boxes the sensors go in have got much better. And normally we ask for a 5-year operation and maintenance period from the contractor installing the equipment. So that's the sort of cycle. The sealant, the detail that we've come up with the sealant hides the sealant from the environment, so it should last. That joint detail should last as long as cable guard lasts.
Richard Gustatus, Mistras. With regards to the sensors that you're putting in for the dehumidification, have you guys ever seeded anything across the cross section? Because depending on the diameter, the cable, whether it's 20 inches or 32, to see how long, like especially for moisture that could be in the center of that cable to actually get out, or if that moisture just kind of sits there and all you're drying out is the outside area.
I think the cable diameter doesn't really make a difference that I've seen, Richard. I think it all depends on the cable construction and the amount of corrosion product in there. There are a couple of oiled cables which are a challenge, Ben Franklin, Bronx Whitestone, and others that have been oiled, but there's been some good work done by Columbia to show that even in an oiled cable, which has been filled with oil, albeit it was new oil, you will get eventually, if there are spaces within that cable, then the mechanism is that the air will dry out. That's almost guaranteed that will happen. But I don't think cable diameter really has a big effect on it.
I was just wondering if you were aware of the Columbia.
No, I haven't come across that before.
Hand for Barry.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.